Decarbonizing the UAE's building stock. Retrofit optimization through 3D printed green shading by Maria Martins and Tala Fawaz. The UAE is a rapidly growing country that views sustainability as a pillar for its development. As an established global leader in the field of architecture, the nation has embedded its environmental responsibility into law. Today, the Estadema Pro rating system has turned performance-efficient construction into a standard for every new project. And with the current rate of development, the sustainable initiatives in place will have cascading impacts in the country. However, the problem lies in the fact that Estadema was only established in 2010. This means that the building stock that predates it fails to meet modern energy performance standards. And as pre-2010 construction represents a very large portion of the UAE urban fabric, these aging buildings are a substantial obstacle in achieving the Net Zero 2050 goal. Not only this, the building sector accounts for almost 70% of total electricity demand. And while retrofitting interventions like shading are implemented to subdue this, most rely on materials like aluminum that trade operational savings for a high carbon investment that can take decades to repay. So, despite the urgent need to improve the legacy building stock, there is a critical gap in research into low carbon retrofit alternatives that are optimized for regions like Abu Dhabi. To thoroughly dissect this, we performed a comparative analysis of shading device materials, evaluating 100% recycled aluminum versus 3D printed ASA with basalt fiber reinforcement. So what is this novel material? Well, on its own, ASA is a known thermoplastic with extremely weather and UV resistant properties. It is widely used in additive manufacturing with recent applications for components like bridges and facades. In order to make ASA stronger for such uses, it is commonly reinforced with glass or carbon fibers. But recent studies have found a sustainable alternative that is made from melted volcanic rocks. The basalt fibers, or BF for short, have nearly the same properties as the glass and carbon options while costing around 8 times less. Studies also show that BF reinforcement in ASA can reduce the coefficient of thermal expansion by up to 75%, which virtually eliminates warping, making this material ideal for a shading component under the Abu Dhabi sun.
To answer the research question, the project begins by establishing a generic pre-Estadema office building and analyzing its energy consumption. We then applied a standard retrofitting bundle with strategies common here in the UAE. Although we mean to focus on optimizing shading devices specifically, retrofitting interventions are rarely implemented on their own. So we aim to comprehensively study how retrofitting actually affects energy use. For Phase 3, we proposed a new shading device material, ASA with basalt fibers, to substitute the traditional aluminum devices. We then analyzed how this material choice shapes the balance between embodied and operational carbon. Lastly, we evaluated how these strategies remain effective under future UAE energy scenarios. And so, the variant models were developed using Autodesk Revit. Energy simulations were done with OpenStudio, followed by lifecycle assessment, one-click LCA, to quantify embodied carbon. Finally, the results were compared. The B0 variant represents pre-Estadema office buildings with typical construction and high energy demand. It is modeled as an 8-story reinforced concrete structure with a slab and core system, a 50% window-to-wall ratio, and envelope properties reflecting low insulation standards of that period. The R1 variant applies a standard retrofit bundle using conventional recycled aluminum shading, along with cool roof coatings and standard HVAC and lighting system optimizations. The R2 variant applies the same retrofit strategies but replaces aluminum shading with 3D printed ASA-BF devices.
As mentioned, variants R1 and R2 have the same shading devices, but with different profiles due to the material. R1 with aluminum follows industry conventions, but since ASA-BF is a novel material, we calculated its thickness based on the requirements of the local building code. This established R2 solid, a 70mm solid profile, as the minimum structural benchmark. For the R2 Sailor variant, we leveraged the geometric freedom of additive manufacturing to optimize the use of material. Research pointed that an internal honeycomb profile at 30% infill density provides the best strength-to-weight ratio for ASA. This geometry reduced the total shading mass by 35% in comparison to the aluminum variant R1, and this reduction has direct implications in the carbon footprint of the shading system.
The evaluation covers a 50-year period and utilizes a hybrid lifecycle approach. The first two variants are assessed from production to demolition, evaluating both embodied carbon and operational energy, whereas the R2 variant is assessed only from production stage, focusing on the embodied carbon of early stages due to lack of maintenance and end-of-life data for the noble material.
According to local manufacturers, the recycled aluminum in R1 emits 5.4 kilograms of CO2 per kilogram of shading device produced. And once again, as we're dealing with a new material, there was no detailed data on the carbon footprint of ASABF, so we calculated it through a decomposition method. We accounted for the emissions from the manufacturing of the raw materials to the energy used in 3D printing the final product. Through verified sources, we found that ASABF emits only 1.6 kilograms of CO2 per kilogram of shading device made.
These are the key assumptions used in operational simulation, reflecting local climate conditions, occupancy patterns, and load adjustments. The operational energy and embodied carbon analysis compares the baseline model, B0, with the retrofit scenario, R1. For the baseline, the building shows a high energy use intensity of 133.7 kilowatt-hours per square meter per year. Cooling demand dominates, accounting for roughly 72% of total consumption due to the hot climate and inefficient envelope performance. After applying the retrofit bundle in R1, the building achieves a significant 25.6% reduction in total energy use, lowering the energy intensity to 99.4 kilowatt-hours per square meter per year. The most notable improvement, however, comes from lighting, which is reduced by nearly 59% through the use of LED systems and occupancy sensors. This also contributes indirectly to lower cooling loads by reducing internal heat gains. Cooling demand itself decreases by 22.7%, driven by the combination of external shading, reflective roofing, and optimized HVAC operation. Overall, the retrofit results in annual energy savings of approximately 487,000 kilowatt-hours, demonstrating that integrated low-intervention strategies can significantly improve building performance in the UAE context. As for embodied carbon, the reduction in operational energy over a period of 50 years results in 22.7% embodied carbon savings.
Moving from an aluminum shading system to solid ASABF significantly lowered our carbon footprint. But by utilizing a cellular profile, we pushed those savings to an 80.8% reduction in carbon emissions. As the UAE grid decarbonizes, operational emissions naturally decrease, making the upfront carbon of materials the primary driver of a building's global warming potential.
ASABF is a scalable and affordable solution that can be replicated and adapted across multiple buildings and contexts while improving energy performance and maintaining architectural identity. While acknowledging limitations in lifecycle scope and current technology adoption, the findings demonstrate clear potential as an environmental solution. By combining material innovation through ASA basalt fiber with the geometric freedom of 3D printing, we align with the UAE national policy, delivering a massive 80.8% saving in embodied carbon and a 25.6% reduction in operational energy use.